Okay, in this video, let us see what is Miller's theorem and why this Miller's theorem is so important in frequency response of amplifiers. Uh, of course, in 1910s, maybe a century back, Miller has came up with a solution for any impedances that are connected between two voltage sources. Now this is a floating impedance between V1 and V2. Of course, V1 is the nodal voltage at node number 1. At node number 2, V2 is the nodal voltage, and between V1 and V2 we have an impedance ZF. So this is ZF is the impedance that is there between this and this. Now using Miller's theorem, we can replace this ZF, which is floating between 1 and 2, as a impedance Z1 at the node number 1, and at this point it is represented by Z2. So this is node number 2. This is actually V1 voltage, this is V2 voltage. No change in this nodal voltages. This is V1 at node 1, at node 2 it is V2. This ZF is now replaced by Z1 between node 1 and ground. Z2 is between node 2 and ground, and these two are 100% equal. If the current that is flowing here, so which I'll call it as IF, flowing through the floating capacitance, if that is equal to this I1, this is what is IF, which is leaving the node. If the same current is leaving here, so I1 is equal to IF now. I1 is equal to IF. If I1 is equal to IF, then Z1 actually represents the equivalent of ZF. And the same IF is entering the node V2, and we are considering a node here. So let me take it as I2. So now if this I2 is in the opposite direction equal to IF, suppose if I2 is equal to minus of IF, because they're in the opposite direction, you can see this is entering the node, this is leaving the node, whereas here IF was leaving, this is also leaving. So that's why these two are in same leaving current. If the leaving currents are equal and this is entering current, this is leaving current. So how do I write this as an entering current? I'll write it as minus of I2. So that's what is minus of I2 or minus of IF. So now if I equate these two, then I'll get the equivalent of Z1, Z2 in terms of ZF. So now what is actually IF? IF is the current flowing in this ZF with a potential difference of V1 minus V2. So now since we are considering that current is going from V1 to V2, so it is V1 is at higher potential minus V2 divided by ZF. So what is this? Is equation number 1. Then what is I1? I1 is the current flowing from V2 to ground with the impedance of Z1. So is it not V1 by Z1? This is equation number 2. What is I2 is equal to? I2 is equal to V2 by Z2. This is equation 3. So use 1, 2, 3 equation and try to equate them here. So using this equation A, which uses equation 1 and equation 2, can I write this as V1 minus V2 by ZF is equal to, that's what is this, okay, IF is equal to, what is I1? I1 is equal to actually V1 by Z1, or I can just the other way also. So it is V1 by Z1 is equal to V1 minus V2 by ZF. So let me write this as it is. So this is I1, this is IF. So can I now write, I will write 1 over Z1 is equal to, so shall I write it as 1 over ZF into V1 minus V2 by V1. I can write this. I will just reverse everything. So shall I now write it as Z1 is equal to ZF V1 by V1 minus V2. This I can easily write mathematically. So this is my equation I have. So what I'll do, I will take out V1 common factor. Can I now write Z1 is equal to ZF divided by 1 minus V2 by V1. If I take V1 outside, so then V1 also comes outside. This will become 1 minus V2 by V1. So this is so and so. So now what is this V2? V1. So this is V2, this is V1. Suppose you consider this as output, this as input. If this is input, this is output. So what is this? Is it not output by input? So what do we usually say output by input in terms of voltage ratio? Is it not the gain of the amplifier or gain of the circuit? So I will write Z1 as equal to ZF divided by 1 minus AB. 1 minus AB. So this is the expression I have. So meaning, if you have a floating impedance ZF, it can be replaced by a resistance connected from node 1 to ground with Z1. So this will be the representation of this ZF if Z1 is equal to ZF by 1 minus AB, where AB is V2 divided by V1. So this is what is Z1 and ZF relation in terms of AB. So let us equate this I2 and minus IF and get the relation between Z2 and ZF. So what is this equation we have? We have the equation I2 is equal to minus of IF, where I2 is given by V2 by Z2 and minus of IF is minus of V1 minus V2 by ZF. So if I rewrite this, it is V2 by Z2 is equal to V2 minus V1 by ZF. So I'll just multiply this. So now can I now write Z2 is equal to ZF multiplied by V2 by V2 minus V1. So can I now write Z2 is equal to ZF, taking V2 as common factor, is it not 1 minus V1 by V2? So now what is this V1 by V2? It's actually 1 over the voltage gain. So actually V2 by V1 is AV, but V1 by V2 is 1 over AV. So can I now write Z2 is equal to ZF by 1 minus 1 over AV. This is what is Z2. What was Z1? Z1 was equal to ZF multiplied by, this is what we had, ZF divided by 1 minus AV. Correct? So this is the expression for Z1 and Z2 in terms of okay, these two are the equation. This is Z2, that is Z1. So this is in terms of impedances. In our capacitors, what we have is, so we have maybe when we actually looked into the parasitic capacitance, so there will be a parasitic capacitance between gate and source. So this is gate and drain. So this we call it as CGDO or CGD, between gate and drain. So this is the one which is the floating capacitance between the two nodes. So this is your input node, this is your output node. I want to replace this CGDO, which is between this and this, as one capacitance here and other capacitance here. So this I want to replace it as C1, say it as C2. This capacitance which is between input and output will be represented as two capacitance, one at the input side, one at the output side, where C1, now this is like your ZF, this is like your Z1, this is like your Z2. So it is as simple as that. Can you see here? Is it analogous to this? So this is what we had. So there is a ZF between V1 and V2. So here I have some impedance which is in the form of capacitance between V1 and V2, which is nothing but input output. So this is now replaced by one impedance between input and ground. That's what is this, one capacitance between input and ground, and other capacitance between V2 and ground. So this is V2, which is your output in your case. So this and ground. So this is what is C1, C2. Now we know the expression for Z1, Z2 in terms of ZF and AV. So now in this case, what is ZF is equal to, ZF is actually equal to XF, which is nothing but 1 over 2 pi CGD into F. So let me not write CGDO. So this is a capacitance in general between gate and drain. So now shall I say this ZF is equal to 1 over 2 pi CGD into F. Then what is Z1? Is it not equal to 1 over 2 pi C1 into F? C1 into F. So what is Z2? Is it not 1 over 2 pi C2 into F? So wherever Z is there, replace it by X. That X is replaced by 1 over 2 pi, because we know that reactance offered by the the capacitor is 1 over 2 pi F into C. F into C. So this is all Z1, Z2, ZFs. Now let us use those Z1, Z2, ZFs to find what is C1 in terms of CGDO and so on. So what is Z1 is equal to, so in place of Z1, shall I write it as 1 over 2 pi. Okay, let me use this equation, first equation, and Z1 is 2 pi F C1 into F is equal to, what is ZF? ZF is 1 over 2 pi CGD into F divided by 1 minus AV. What is AV in case of your amplifier now? AV in case of amplifier, actually the AV is actually minus GM into RD, minus GM into RD. So now if you actually substitute the gain of the amplifier, is it not minus of AV what you have? Is it not minus of AV? Why it is minus of AV? The actual gain of the amplifier, which is V0 by Vin, is actually minus GM into RD. So this is actually so and so. So does this, sorry, this 2 pi and F, 2 pi and F, will it go off here? So what do you have now? So don't you have now this as 1 over C1 is equal to 1 over CGD into 1 plus AV. So this is AV magnitude, which is GM into RD. So now, so can I write this C1? So using this, from this equation, can I write C1 is equal to CGD into 1 plus AV magnitude? See now, the only we know how did we write this Z1. Z1 is so and so, Z2 is this. Now we are taking that impedance, let it be capacitive, so that ZF is X of S, where X of S is 1 over 2 pi into C into F, which C, so now floating capacitance is between gate and drain, so that's why it is CGD. So this what is CGD, and what is Z1? We say it as let it be C1, so it is so and so. Then we use this equation, try to find out what is C1 is. So this 2 pi F goes on, which is there on either side. Upon simplifying, you got the expression for C1 here as equal to CGD, which is the floating capacitance, multiplied by 1 plus AV, where this AV is the magnitude of this gain of the amplifier, which is GM into RD, which is GM into RD in case of lambda not equal to 0. If it is not there, of course, we write it as GM into RD parallel R naught, RD parallel R naught. This is what is C1 is. But how about C2? C2 is as simple as this. So let me write what is Z2 is equal to. This is my Z2 value. Z2 is equal to ZF by 1 minus 1 over AV. In place of Z2, shall I write it as 1 over 2 pi F into C2. In place of ZF, shall I write it as 1 over 2 pi F into CGD divided by 1 minus 1 over, What is this AV? So AV is actually minus AV. Minus AV is because it is minus GM into RD. So this minus and minus will go off. So this will become plus. So now does this go with this? So do you have 1 over C2 is equal to 1 over CGD into 1 plus 1 over AV magnitude. So then what is C2? C2 is equal to CGD into 1 plus 1 over AV. So this is the expression for the C2 capacitance which will going to come here on the second node. So this is what is C2. Of course, we already found that C1 is equal to same CGD, but it is 1 plus AV. 1 plus AV. So this is what is C1. That's why in the small signal model, we replace this floating capacitance which is there between gate and drain. So this gate and drain capacitance will be replaced by a capacitance which is there. Okay, that's what you can see here. So if you just see, so this is in the textbook. Maybe you can just look at this section 11.1.5 Miller's theorem. He talks about the same thing. He just refers to this capacitance. Let me show you that. He is just referring to, okay, where is that? He is just referring to this CF. CF is the capacitance between input and output. So this CF, a capacitor with floating capacitor, will be replaced one C1 here, the other one C2 there. So that's what he is trying to say here. That's what is, can you see here? This is C1. This is, of course, this is a capacitance which is floating, having a gain of minus A0. In our case, it is minus GM into RD. So at the input side, you are replacing it by CGD into 1 plus AV, and this is CGD into 1 plus 1 over AV. So this is what is A0 is the actual gain of the amplifier. Of course, it is minus of A0. You are writing it as just the magnitude. This is how we will write. That's what is here. If you can see there, can you see here? This capacitance CF will be split into C in and C out. So what is C in? C in is equal to this CF into 1 plus AV. That's what is this here. Can you see this is C in is equal to CF into 1 plus A0. A0 is the gain of this amplifier. Of course, that A0 is actually, you can see it is GM into RD. GM into RD. So that's what you have here. Maybe just let me just do this here. See here, this is A0, which is the magnitude GM into RD. But what is C out? C out, as we know that it is, this is what is C out. This is what is C out. This is actually CG, that is CF, which is CGD multiplied by 1 plus 1 over AV. 1 plus 1 over AV. This is what we have discussed in the class. So this is how we can able to understand this. Okay, we will take up some problems in the next video and try to use this Miller concepts theorem to find out the bandwidth of an amplifier and find out what is the gain bandwidth product of the amplifiers. Thank you.